Welcome to Nimo's World. It's me Nimesh Naik. Today I am discussing IIT-JAM questions. Topic Linear Algebra under the section Theory of Matrices and System of Linear Equation. That is, we are discussing the questions from the area Theory of Matrices and System of Linear Equation. So first we are solving JAM questions of 2019. First question. Let P be a 3 by 3 non-null real matrix if there exists a 3 by 2 real matrix Q and a 2 by 3 real matrix R such that P is equal to QR, then option A, Px is equal to 0 has a unique solution where 0 belongs to R3, and option B, there exists a B belongs to R3 such that Px is equal to B has no solution, and option C, there exists a non-zero B belongs to R3 such that Px is equal to B has a unique solution, and option D, there exists a non-zero B belongs to R3 such that P transpose X is equal to B has a unique solution. So this question is relating to the area system of linear equation. Here we can give a system of homogeneous equation, also system of non-homogeneous. So we want a just idea about that system of linear equation. So before going through the question, first of all we want to know some result relating to the rank of matrix. So result, let A comma B belongs to M by N of R, that is A B belongs to M by N matrices of real entries. Result A, rank of A which is less than or equal to minimum of M comma N, and rank of AB which is less than or equal to minimum of rank of A comma rank of B. Now we want to know some results about system of linear equations. So result, let A belongs to M by N of R, and X belongs to Rn and B belongs to Rm. Then for a non-homogeneous system of equation, Ax is equal to B, which is a matrix equation, Ax is equal to B where B not is equal to 0. Then first one, the system is said to be consistent if rank of A is equal to rank of the augmented matrix A with B. And second result, the system has a unique solution if and only if rank of A is equal to rank of the augmented matrix A with B, which is equal to N. That is the number of unknowns, full rank. Okay. So if the system is said to be inconsistent if rank of A not is equal to rank of the augmented matrix A with B. If the system is said to have a solution, that means the system is consistent. That is, a system is said to be consistent if rank of A is equal to rank of A with the rank of the augmented matrix rank of A with B. Now we have another result. Let A belongs to M by N of R, and X belongs to Rn and 0 belongs to Rn. Then for a homogeneous system, Ax is equal to 0. First one, rank of A is equal to rank of the augmented matrix A with the 0 matrix, then the system is always consistent. That means a homogeneous system of linear equation is always consistent. And result number 2, if rank of A is equal to N, then the system has a unique solution. That is, if rank of A is equal to the number of unknowns, then the system of linear equation, system of homogeneous linear equation has a unique solution. And also we have a result. For a real matrices, rank of A is equal to rank of A transpose. A transpose is the matrix obtained by interchanging the row and columns of A. Okay, so that are the results. Now we are going through our question, and first of all we are analyzing our question. So given that P be a 3 by 3 matrix, and also given that non-null real matrix, that is non-zero real matrix. So P be a 3 by 3 non-zero real matrix, and given that Q be a 3 by 2 matrix and R be a 2 by 3 matrix. Now we are computing, now we are analyzing the rank of Q and rank of R. So we are getting an idea about the rank of Q and rank of R. So here rank of Q which is less than or equal to minimum of 2 comma 3. That is, we are using the previous result, rank of A which is less than or equal to minimum of m comma n for a m by n matrix. So using that we get rank of Q which is less than or equal to minimum of 2 comma 3, which implies that rank of Q which is less than or equal to 2. That is the minimum of 2 and 3 which is 2. So we can say that rank of Q which is less than or equal to 2. Similarly, the rank of R which is less than or equal to minimum of 2 comma 3, which implies that rank of R which is less than or equal to 2. Since R is a 2 by 3 matrix, so by that using that result, rank of R is equal which is less than or equal to minimum of 2 comma 3, which implies that rank of R which is less than or equal to 2. So we have get rank of Q which is less than or equal to 2 and a rank of R which is less than or equal to 2. Now we have given that P is equal to Q of R. So here we want to find or we want to analyze the rank of P. For that, first we are finding the rank of Q and rank of R. So we can given P is equal to QR and we have given P is equal to QR. Then rank of P is equal to rank of QR, and which is less than or equal to minimum of rank of Q comma rank of R. That is, we are using our first result, the rank of P which is equal to rank of QR, which is less than or equal to minimum of rank of Q and rank of R. And also we have given that, also we get that rank of Q which is less than or equal to 2 and a rank of R which is also less than or equal to 2. So from that we can conclude that rank of QR which is less than or equal to 2 and a rank of QR is equal to rank of P. Therefore we can say that rank of P which is less than or equal to 2. That is, we can get rank of P which is less than or equal to 2. So now we are going through our options. Our first option, which says that Px is equal to 0, has a unique solution where 0 belongs to R3. So Px is equal to 0, which is a homogeneous system of linear equation. So for a homogeneous system of linear equation which has a unique solution, means that rank of that matrix, that is rank of the coefficient matrix, rank of P, which is equal to the number of unknowns. Okay, so here we have P is a 3 by 3 matrix, and by this condition, that is, we have given that Px is equal to 0 as a unique solution. That is, unique solution means that rank of P is equal to the number of unknowns. Since P is a 3 by 3 matrix, so here the number of unknowns is 3. Therefore we can conclude that rank of P which is equal to 3. So if Px is equal to 0 has a unique solution, then rank of P is equal to 3. But here we arrived at rank of P which is less than or equal to 2. So we have rank of P less than or equal to 2. But if Px is equal to 0 has a unique solution, then rank of P is equal to 3. So we get a contradiction, which is not possible, because the rank of our P must be less than or equal to 2. That is, rank of P is equal to 0 or 1 or 2. That cannot be 3. Therefore, this condition is not possible. That is, Px is equal to 0 has not unique solution. Therefore, our first option is wrong. Now we are going to our third option, which says that there exists a non-zero B belongs to R3 such that Px is equal to B has a unique solution. So we have given that Px is equal to B has a unique solution. Also it's a non-zero B belongs to R3. Given that non-zero B belongs to R3, that means this system is a non-homogeneous system of linear equation. So for a non-homogeneous system of linear equation has a solution, means rank of A is equal to rank of the augmented matrix. Here we are using P. So here we have the coefficient matrix is P. So here we can say that rank of P which is equal to rank of the augmented matrix P with B. Okay. So, and which is also say that which has a unique solution. So our previous note, we can say that if it has a unique solution, rank of P is equal to rank of the augmented matrix is equal to n, the number of unknowns. So here P is a 3 by 3 matrix, so we can say that here that number of unknowns is 3. So we are again taking this statement, Px is equal to B has a unique solution. Px is equal to B has a unique solution implies that rank of P, which is equal to rank of the augmented matrix P with B, which is equal to 3. So but we have rank of P which is less than or equal to 2. We are already computing that rank of P which is less than or equal to 2. And if it has a unique solution, then rank of P is equal to 3. So which is not possible. So our option, third option, is also wrong. Now for the fourth option, it says then there exists a non-zero B belongs to R3 such that P transpose X is equal to B has a unique solution. Also note that there exists a non-zero B belongs to R3. So this system P transpose X is equal to B is a non-homogeneous system of linear equation. For it has a unique solution. First of all, it has a solution. Solution means that the system is consistent. System is consistent means that rank of P transpose is equal to rank of the augmented matrix P transpose with B, and it is a unique solution, which implies that that must be equal to the number of unknowns. Okay, so we have the result for a real matrix rank of P which is equal to rank of P transpose. For a real matrices, rank of P and rank of P transpose are same. So we can get we have rank of P which is less than or equal to 2. So rank of P less than or equal to 2 means that rank of P transpose which is less than or equal to 2. Therefore we have rank of P transpose which is less than or equal to 2. So we have given that P transpose X is equal to B has a unique solution, which implies that rank of P transpose is equal to the rank of the augmented matrix P transpose with B, which is equal to 3. But we have rank of P transpose is less than or equal to 2 by the previous same argument that we used previous cases also. Therefore we can get rank of P transpose that is we have rank of P transpose which is less than or equal to 2. But if it has a unique solution, that is the system P transpose X is equal to B has a unique solution, implies that rank of P transpose is equal to 3, which is not possible. So our fourth option is also wrong. Now our previous three options are wrong. Therefore our second option is automatically correct. That is, there exists a B belongs to R3 such that Px is equal to B has no solution. That is, this is has no solution. This is a true statement. So the correct option of this question is option B. For that, it is a non-homogeneous system of equation Px is equal to B, which has no solution by choosing by choosing n B such that rank of the matrix P which is not is equal to rank of the augmented matrix P with B. By choosing like a B, we have get that system Px is equal to B has no solution. So the correct option of this question is option B. Okay, now we are going to the next question. Our next question is, if given a 3 by 3 matrix, if root 5 by the matrix root 5 by 3 minus 2 by 3 C and 2 by 3 root 5 by 3 D A B 1. Okay, so we have given a 3 by 3 matrix and also given that is a real orthogonal matrix. Then we want to find a square plus b square plus c square plus d square is dash. Okay, so we have given a 3 by 3 matrix and also given that it is a real orthogonal matrix. And then we have to find a square plus b square plus c square plus d square. So we have only the hint is it is the given matrix is a real orthogonal matrix. So first of all we want to know what is an orthogonal matrix. So definition for orthogonal matrix: A belongs to Mn of R is said to be orthogonal if A transpose is equal to A transpose A is equal to I. Okay, so a matrix is said to be orthogonal if A into A transpose, which is equal to A transpose into A, which is equal to I. So we have only the given, we have only uh, this criteria. So by using this, we want to find A square plus B square plus C square plus D square. So we are let this the given matrix be A. So A is equal to the 3 by 3 matrix root 5 by 3 minus 2 by 3 C 2 by 3 root 5 by 3 D A B 1. So given that A is a real orthogonal matrix. So by using the real orthogonal matrix, we are finding the value of A square plus B square plus C square plus D square. Since A is a real orthogonal matrix, we have A transpose is equal to I. So we are first finding our procedure is like, first we find A transpose, then we computing A transpose, and it is equating with I. Then we get A square plus B square plus C square. Then we get the value of A square plus B square plus C square plus D square. Okay. So now A transpose is equal to, by interchanging the row and columns of A, we get A transpose. So here A transpose is equal to root 5 by 3 2 by 3 A and minus 2 by 3 root 5 by 3 B and C D 1. Now we are computing A transpose. So A transpose is equal to 1 root 5 by 3 minus 2 by 3 C 2 by 3 root 5 by 3 D A B 1 into matrix root 5 by 3 2 by 3 A minus 2 by 3 root 5 by 3 B C D 1. Now we want only the diagonal elements, so I just computing that diagonal elements only. The rest of element, if you want, you will must compute the rest of this the rest of elements. We for computing the value of A square plus B square plus C square plus D square, we only want the diagonal elements. So just I calculating the diagonal elements only here. So by operating these two matrices, we get the diagonal entries by 5 by 9 plus 4 by 9 plus C square. That is first row into first column. By doing this, we get this. Now the second diagonal element 4 by 9 plus 5 by 9 plus D square, and the third diagonal element A square plus B square plus 1. So are these diagonal elements containing the terms of C? First diagonal element containing the term of C square, and second diagonal element containing the term of D square, and the third one is containing A square plus B square. Now we have the condition. We have know that A is a orthogonal matrix. A is an orthogonal matrix implies that A transpose is equal to I. So we are using that, we are computing these values. So we are A transpose is equal to I, and we are comparing this matrix A transpose with our identity matrix. So identity matrix is a diagonal entries 1 1, and the rest of that elements are 0 0. So by comparing this element, so this with the identity element, this with the this element with the 1, that is by comparing A transpose with I, in I the first entry is 1, so we get 5 by 9 plus 4 by 9 plus C square is equal to 1, and all the diagonal elements of I is 1, so we can get this element is equal to also 1, and this element is also equal to 1. So we get 4 by 9 plus 5 by 9 plus D square is equal to 1, and A square plus B square plus 1 is equal to 1. So put it as first equation be 1, and put it as this is equation number 2, and this is equation number 3. So from the equation number 1, we get 1 implies that is we have 5 by 9 plus 4 by 9 plus C square is equal to 1. From this we get C square is equal to 1 minus 5 by 9 minus 4 by 9, which is equal to 1 minus 9 by 9, that is this term is 1, that is 1 minus 1, which is equal to 0. And from the equation number 2, that is the equation number 2 is 4 by 9 plus 5 by 9 plus D square is equal to 1. From this D square is equal to 1 minus 4 by 9 minus 5 by 9, which is equal to 1 minus 9 by 9, which is equal to 0. Okay, that is we get a d square is equal to 0 and c square is equal to 0. Now from the equation 3, a square plus b square plus 1 is equal to 1. From this we get a square plus b square which is equal to 1 minus 1 which is equal to 0. Therefore we get a square plus b square is equal to 0. That is we are getting c square is equal to 0 and d square is equal to 0 and a square plus b square is equal to 0. Therefore a square plus b square plus c square plus d square is equal to, then a plus b whole square is equal to 0 and c square is equal to 0 and 0. So whole sum becomes 0. Therefore we get a square plus b square plus c square plus d square which is equal to 0. So our required answer is 0. Now our third question, which says that if AD minus BC is equal to 2 and PS minus QR is equal to 1, then the determinant of this matrix AB 0 0 3 10 2P Q C D 0 0 2 7 2R S is equal to dash. That is, we want to compute the determinant of this 4 by 4 matrix. And we have given that AD minus BC is equal to 2 and PS minus QR is equal to 1. So we are just expanding, just computing this determinant by then expand that determinant, then we get the terms of AD minus BC and PS minus QR, then we substituting the values in that region, therefore we get the required answer. It's a 4 by 4 matrix, so the determinant is much more difficult, but here we have the entry, this entry and this entry is 0, so we have to only the entries corresponding to A and corresponding to B in the determinant, so it is must be easiest question. So for that we first of all can't find the determinant. So the determinant of this matrix is equal to A B 0 0 3 10 2 P Q C D 0 0 2 7 2R and S. So for first computing for the corresponding first element, so A into and eliminating the row and column, this column and this row can be eliminated, and the determinant of the remaining portion. So A into determinant of 10 2P Q D 0 0 7 2R S and minus B into, so B into determinant of that the remaining, that is we are eliminating this column and this row and the rest of this element, determinant of the rest of this portion. So minus B into determinant of 3 2P Q C 0 0 2 2R S. So which is equal to A into determinant of this. So determinant of this means 10 into the determinant of this portion. So 10 into 0 and minus 2P into eliminating this column and this row. So D into S minus 7 into 0. So minus 2P into DS. So similarly Q into eliminating this column and this row, so determinant, then determinant of this portion, so D into 2R minus 7 into 0, so which will become Q into 2DR. Similarly we are computing the determinant of this portion, so which is equal to minus B into 3 into 0 minus 2P into CS plus Q into 2CR. Now we are just open the bracket, then we get minus then we get minus 2 APDS plus 2 AQDR plus 2BPCS minus 2BQCR. That is the first term will become 0 and this term will be also 0, then the remaining terms. So by looking the first two terms, so here minus 2 is common and A is there and D is there, and also in this term and 2 is there, A is there and D is there. So I taking a minus 2 AD is common, so we get minus 2 AD into the remaining portion, then P into S, so PS minus here we plus term, so taking a minus, so here minus 2 minus into the remaining terms Q and R, so minus Q. So we the first term become minus 2 AD into PS minus 2R plus here 2 is here, B is here, C is here, and also in this term 2BC is also here. So take it outside. So I taking 2BC outside, then the remaining term is PS minus QR. Okay, that is we get minus 2AD into PS minus QR plus 2AB 2bc into ps minus qr. And we have given from the question ps minus qr is equal to 1. So substituting here 1 and also substituting ps minus qr is equal to 1. So we get a which is equal to minus 2ad plus 2bc. That is this term become 1. So minus 2 into ad into 1 and also but here 2bc into 1. So we get minus 2ad plus 2bc. So here from this we are taking a minus 2 common outside. So minus 2 into ad minus bc. So we are getting my ad minus bc, and also from the question it is given that ad minus bc is equal to 2. So substituting ad minus bc is equal to 2 here. So we get minus 2 into 2, so which is equal to minus 4. That is we get the determinant of the given 4x4 matrix is minus 4. So we get the determinant of the given matrix is minus 4. Okay. Now next question. Consider the following system of 3 linear equation in 4 unknowns x1, x2, x3 and x4. So the system of linear equation is x1 plus x2 plus x3 plus x4 is equal to 4, and x1 plus 2x2 plus 3x3 plus 4x4 is equal to 5, and x1 plus 3x2 plus 5x3 plus kx4 is equal to 5. Then if the system has no solution, then find the value. K is equal to dash. So we have given a system of linear equation, that is a 3 system of linear equation with 4 unknowns, and also it is a non-homogeneous system of linear equation, and given that the system has no solution. The system has no solution means the system is inconsistent. The system is inconsistent means the rank of the coefficient matrix which is not is equal to the rank of the coefficient matrix with respect to rank of augmented matrix. Okay. So before going through the question, we state a result. Let A belongs to M by N of R, and X belongs to Rn and B belongs to Rm. Then the non-homogeneous system Ax is equal to B, that is the matrix representation of a homogeneous system. B not is equal to 0, has no solution if rank of A which is not is equal to rank of the augmented matrix A with B. That is, here we can given a system of linear equation, and we can replace it into a matrix equation, that is Ax equal to B. So here we taking the coefficient matrix into x1, x2, x3, x4 which is equal to 4, 5, 5, that is B, that matrix, and x B the column matrix, x1, x2, x3, x4. Okay. Now we are going to our question. First of all, we want to find the rank of our augmented matrix. So our augmented matrix is like this. Augmented matrix AB is equal to 1, 1, 1, 1, 4, 1, 2, 3, 4, 5, 1, 3, 5, k, 4. So this is the coefficient of our equation. The augmented matrix can be written by the coefficient. The first row is the coefficient of x1, x2, x3, x4. That is our first row of our augmented matrix, and the corresponding b value is here, like the rest of these elements. So we get the augmented matrix AB is equal to this matrix, and which is similar to here we are applying the row operations. We are row reducing means so where R2 changes to R2 minus R1 and R3 changes to R3 minus R1. So we get the first row is same 1, 1, 1, 1, 4, and the second row which will changes to R2 changes to R2 minus R1. So here 1 minus 1 0, and 2 minus 1 is equal to 1, and 3 minus 1 is equal to 2, and the rest of this element. And similarly R3 we get a 0, 2, 4, k minus 1 and 1. Now we are again applying the row operation. R3 changes to R3 minus 2 R2. So the first two row are remaining same 1, 1, 1, 1, 4, 0, 1, 2, 3, 1, and the third row which we are applying R3 changes to R3 minus 2R2. So it will become 0, 0, 0 and k minus 7 and minus 1. And now in the question we have given that our system has no solution. System has no solution means rank of the coefficient matrix which is not is equal to the rank of augmented matrix. So we are considering this portion first, this portion first, and this. If we have this entry is equal to 0, so the last row of this matrix must be equal to 0. So the rank of this portion, rank of this matrix must be equal to 2. Then if we are considering this column, then we have the rank is equal to 3, because here we have a non-zero entry minus 1, and if k is equal to 7. Okay, so that is our idea. So for making rank of A, which is rank of the coefficient matrix which is not is equal to the rank of the augmented matrix, that is we are doing. So given that the system has no solution, that is rank of A not is equal to rank of the augmented matrix A with B. That is if k is equal to 7, that is if k is equal to 7, if k is equal to 7, this entry must be 0. So the rank of this matrix is 2 and the rank of the augmented matrix is 3. That is we have get a rank of A is equal to 2 and a rank of A augmented matrix A with B is equal to 3. That is rank of A is equal to 2, which is not is equal to rank of the augmented matrix A with B, which is equal to 3. Therefore we have no solution. That is the system is inconsistent. The system is inconsistent means system has no solution. System is consistent if rank of A is equal to the rank of the augmented matrix. That is if the system has no solution, then k is equal to 7. So our value of k is 7. Okay. Now our next question, which is question, let M and N be any two 4x4 matrices with integer entries satisfying Mn is equal to 2 into this matrix 1 0 0 1 0 1 1 0 0 0 1 0 0 0 0 1. Then the maximum value of determinant M plus determinant N is dash. So we have given that M and N are two 4x4 matrices and Mn is equal to this matrix, and we want to find the maximum of determinant M plus determinant N. Okay, so here for solving this question we want some result. So the first result is eigenvalues of a triangular matrices are exactly the diagonal entries. So for a triangular matrix, the eigenvalues are the diagonal entries. And result number 2, let A comma B belongs to Mn of R, then determinant of AB is equal to determinant A into determinant B. That is determinant AB is equal to determinant A into determinant B. And next result, if lambda 1, lambda 2, etc. to lambda n are eigenvalues of A belongs to Mn of F, F be a field need not be distinct, then determinant A is equal to product I range from 1 to n lambda I. Okay, that is lambda 1, lambda 2, etc. to lambda n are an eigenvalues of A which belongs to Mn of R with a field F. So the determinant A is equal to product of eigenvalues. That is determinant A is equal to the product of all eigenvalues. Now we are going through our question. In our question we have given that Mn is equal to 2 into this matrix 1 0 0 1 0 1 1 0 0 0 1 0 and 0 0 0 1, which is equal to, we are multiplying 2 with this, we get the matrix 2 0 0 2 0 2 2 0 0 0 2 0 0 0 0 2. Okay, so the given matrix, this matrix Mn matrix is a upper triangular matrix with all the diagonal entries are 2. Okay, that is we get the diagonal, all the diagonal entries are 2, and it is an upper triangular matrix. It's an upper triangular matrix, and we have a result for a triangular matrices. The eigenvalues are the diagonal elements. So eigenvalues are the diagonal elements means these eigenvalues for Mn, the eigenvalues of Mn are 2 2 2, 2. Okay, that is we get the eigenvalues of Mn are 2, 2, 2. That okay. And we know that already we know that determinant of Mn, which is equal to product of all eigenvalues of Mn. That is we by our previous note we say that determinant of A is equal to product of all eigenvalues. By using that we say that determinant of Mn is equal to product of all eigenvalues, and here we get the eigenvalues are 2, 2, 2 because it is a upper triangular matrix, so the diagonal elements are the eigenvalues. So we get the determinant of Mn, which is equal to 2 into 2 into etc. 2 into 2 into 2 into 2, which is equal to 16. So we get a determinant of Mn is equal to 16. Also we have the result determinant of Mn is equal to determinant of M into determinant N. That is we are saying that determinant of AB is equal to determinant A into determinant B. By using that we are saying that determinant of Mn is equal to determinant M into determinant N. And we are also computing determinant Mn is equal to 16. So we can say that determinant Mn is equal to determinant M into determinant N is equal to 16. That is we have said that determinant M into determinant N, which is equal to 16. Now we are finding the possible pairs of determinant M and determinant N, because we want to find the maximum value of determinant M plus determinant N. So the possible pairs of determinant M and determinant N are 1, 16. That is 1 into 16 is equal to 16, and 2, 8, which is 2 into 8 is equal to 16, and 4 into 4 is equal to 16. Similarly 8, 2 and 16. So these are the possible pairs of determinant M and determinant N. Then the maximum value from this is the values of determinant M plus N is equal to 1 plus 16 70, and 2 plus 8 is equal to 10, and 4 plus 4 8, and also here 10, and here also 70. Then the maximum value of determinant M plus determinant N is equal to 1 plus 16, which is equal to 70. So we get the maximum value of determinant M plus determinant N is equal to 1 plus 16, which is equal to 70. Now we want to check whether such matrices are exist or not. If such matrices are exist, this must be true, otherwise not. So there exist such matrices since we take M is equal to I and N is equal to the given matrix, M. Okay, that is 2 0 0 2 0 2 2 0 0 0 2 0 0 0 0 2. Okay, then Mn is equal to we want to satisfy our given condition by taking M is equal to I and N is equal to this matrix. We get Mn is equal to I into N, which is equal to 2 times 1 0 0 1 0 1 1 0 0 0 1 0 0 0 0 1. So our given condition is satisfied, and here determinant of I we know that determinant of M which is equal to 1. So we have no, this is equal to 1, and determinant of N is equal to the product of eigenvalues, because it is a upper triangular matrices, so the diagonal elements are the eigenvalues. So determinant is equal to product of eigenvalues. The product of eigenvalues means 2 into 2 into 2 into 2. So we get determinant N is equal to 60. So there exists such matrices M and N such that determinant M is equal to 1 and determinant N is equal to 60, and determinant Mn is equal to 2 times 1 0 0 1 0 1 1 0 0 0 1 0 0 0 0 1. Okay, so all the given conditions are satisfied in the question. Therefore the maximum value of determinant M plus determinant N is 70. So our answer is 17. So here the JAM questions of 2019 under the section theory of matrices and system of linear equations are over. Now we are discussing the same section under the same section, the JAM questions of 2018. Okay, so the JAM questions of 2018 question: First question, let M is equal to the matrix X, Y, Z be an orthogonal matrix with X, Y, Z belongs to R3 as its column vectors. Then Q is equal to X, X transpose plus Y, Y transpose. Then option A is a skew symmetry matrix and option B is a 3 by 3 identity matrix and option C satisfying Q square is equal to Q and D satisfying QZ is equal to Z. So here we can give M is equal to X, Y, Z. Here X and Y are the column vectors which are belongs to R3 and we have given that X is equal to X, X transpose plus Y, Y transpose. So first of all we want to verify whether this Q is Q symmetric or not and Q is identity matrix or not, and I satisfying this condition Q square is equal to Q and Q satisfying QZ is equal to Z. So that is we have to analyze from this question, and also given that it is an orthogonal matrix. So also given that fact our M is an orthogonal matrices. By using the column vectors of M we write this Q is equal to X, X transpose plus Y, Y transpose by using these column vectors. Okay. So first we want some definition. So first the definition of skew symmetry matrices. So A belongs to Mn of R is said to be skew symmetric if A transpose is equal to minus A. That is, a matrix is said to be skew symmetric if A transpose is equal to minus A. And next the definition of orthogonal matrices. Orthogonal matrices. A belongs to Mn of R is said to be orthogonal if A transpose is equal to A transpose A is equal to I. That is, a matrix A belongs to Mn of R is said to be orthogonal if A into A transpose is equal to A transpose into A is equal to I. And also we have M is equal to X, Y, Z is orthogonal, then X transpose X is equal to 1, X transpose Y is equal to 0. Because M is orthogonal, then the columns of A forms an orthonormal basis. That is, the columns of M must be orthonormal. Therefore we can say that X transpose X is equal to 1 and X transpose Y is equal to 0. So these are the results we want to know. Now we are going to our given condition. Now we are analyzing our options. So we have given that Q is equal to X, X transpose plus Y, Y transpose. Here X and Y are the columns of our orthogonal matrix M. Now we want to check whether it is Q symmetry or not. For that we are first finding Q transpose. So we have Q transpose is equal to X, X transpose plus Y, Y transpose all transpose, which is equal to X, X transpose all transpose plus Y, Y transpose all transpose. So which will become X transpose all transpose into X transpose. So X transpose all transpose become X. So this term will be equal to X, X transpose, and here it become Y transpose all transpose into Y transpose, and we have Y transpose all transpose is equal to Y. So that term become Y, Y transpose. That is, we get Q transpose is equal to X, X transpose plus Y, Y transpose, that is equal to Q. That is, we are getting Q transpose is equal to Q. Therefore we cannot, that is, Q transpose cannot be equal to minus Q. That is, we get Q transpose is equal to Q. If Q transpose is equal to minus Q, then we have said that our Q is Q symmetric. But here we get Q transpose is equal to Q. So it is symmetric, but it is not a skew symmetric. Therefore, we say that Q is not a skew symmetric matrix. Our first option, which says that A is skew symmetry matrix, so our first option is also wrong. Okay. Now our second option says that Q is a 3 by 3 identity matrix. So we want to verify whether it is true or not. For that, first of all, we considering an orthogonal matrix. So a 3 by general form of an orthogonal matrix. I taking a general form of an orthogonal matrix. Okay. Now I take because in our question we have given that M is an orthogonal matrix, and using the columns of that orthogonal matrix we are writing Q. So I take M is equal to the matrix cos theta sin theta 0 minus sin theta cos theta 0 0 0 1 be an orthogonal matrices. It is easily verified that A transpose is equal to A transpose A is equal to I. That is, we are multiplying this, we can get the terms. First term cos square plus sin square, when we computing A transpose we get cos square plus sin square theta, so that term will be become 1, and the next term will be cos theta sin theta minus then the next matrix minus sin theta. When adding, then we get an identity matrix. You can easily verify that. So I take M is equal to this matrix, which is an orthogonal matrix. So this column, the columns of M, this must be this column must be X, and this column must be Y, and this column must be Z. Okay. So here we get X is equal to the column vector cos theta minus sin theta 0, and Y is equal to sin theta cos theta 0. Now we are our Q, that is, we have to verify whether our Q is identity matrix or not. So Q is equal to, we have X transpose plus Y transpose. So here X cos theta minus sin theta 0, and X transpose is equal to cos theta minus sin theta 0 plus Y. Sin theta cos theta 0, Y transpose sin theta cos theta 0. Now we are operating, by using matrix operation we get cos theta into cos theta cos square theta, cos theta into minus sin theta minus cos theta sin square theta, minus cos theta sin theta, and cos theta into 0. And similarly the rest of elements we get minus cos theta sin square theta 0 0 0 0 plus by operating this we get sin square theta sin theta cos theta 0 cos theta sin theta cos square theta 0 0 0 0. Okay, then we adding this we get a cos square theta plus sin square theta minus cos theta sin theta plus sin theta cos theta 0 minus cos theta sin theta plus cos theta sin theta sin square theta plus cos square theta 0 0 0 0. Okay, now we know that it's a trigonometric result, cos square theta plus sin square theta is equal to 1. So this term become 1, and this term are cancelled each other, the 0. So the first row become 1 0 0, and these terms are cancelled each other, so the values must be equal to 0. Therefore we here get 0, and this value sin square theta plus cos square theta, which is equal to 1 and 0, and the remaining term 0 0. And so we get Q is equal, therefore we get Q is equal to this matrix 1 0 0 0 1 0 0 0 0, which is not is equal to the identity matrix I is equal to 1 0 0 1 0 0 0 1. That is, when we take MBA orthogonal matrix and we are computing Q, but we cannot get it be a identity matrix. So our third option, which is say that Q is a 3 by 3 identity matrix, so we cannot get Q is a identity matrix. So our third option is our second option is also wrong. Now for the last option, QZ is equal to Z, third option. Now we are computing QZ. QZ is equal to X transpose plus Y transpose into Z. So opening the bracket we get X transpose into Z plus Y transpose into Z. So which is equal to X into 0 plus Y into 0, which is equal to 0, which is not is equal to Z. Okay, that is, here X transpose Z is equal to 0 and Y transpose Z is equal to 0, because we have M is equal to our matrix X, Y, Z, and also given that this M is orthogonal matrix. This M is orthogonal matrix means the columns of X, Y, the columns of these matrices are orthonormal. Orthonormal means that X transpose Z is equal to 0 and Y transpose Z is equal to 0. So here we get this term must be 0, so X into 0, and Y into this term must be 0, so we get Y into 0. So the whole term Z equal to 0. That is, we get QZ is equal to 0, which is not is equal to Z. But our last option is says that QZ is equal to Z. Therefore our last option is also wrong. Now we are computing Q square. Q square is equal to X transpose plus Y transpose into X transpose plus Y transpose. that we are opening the bracket, we get x transpose into x transpose plus x transpose into y transpose, y transpose x transpose, y transpose y transpose. And we also know that our given matrix M is equal to XYZ is an orthogonal matrix. So columns of M must be orthonormal. So therefore we have X transpose is equal to 1 and X transpose Y is equal to 0 and Y transpose X is equal to 0 and Y transpose Y is equal to 1. So here we have the terms X transpose. So this term become 1 and X transpose into Y, this term becomes 0. And y transpose into x, so this term becomes 0 and y transpose into y, so this term become also 1. Therefore this term, the second term and the third term will be 0, so the remaining term is x transpose, so x transpose plus, but here y transpose, therefore we get y transpose, that is q square is equal to x transpose plus y transpose, that is we can get it, which is the definition of q, therefore which is equal to q, that is we get q square is equal to q, that is we are getting q square is equal to q, therefore our q square is equal to q, that is we have get a q square is equal to q. That is our third option, which says that q satisfying q square is equal to q. So we get q square is equal to q. So this is a correct option. So therefore our third option is correct. So the correct option for this question is option C. Okay. Next question. Suppose alpha, beta, gamma belongs to R. Consider the following system of linear equation. X plus y plus z is equal to alpha, x plus beta y plus z is equal to gamma, x plus y plus alpha z is equal to beta. If this system has at least one solution, then which of the following statement is or are true? Okay. So for this system of linear equation, which of the following has an at least one solution? We have given that this system of following equation has at least one solution. Then we want to find which of the following are true. So option A, if alpha is equal to 1, then gamma is equal to 1. And option B, if beta is equal to 1, then gamma is equal to alpha. And option C, if beta is equal to 1, then alpha is equal to 1. And option D, if beta is equal to 1, then alpha is equal to 1. Now we have a result. Let A belongs to M by N of R and X belongs to Rn and B belongs to Rm. Then the non-homogeneous system Ax is equal to B where B not is equal to 0 is said to be consistent if rank of A is equal to the rank of the augmented matrix A with B. That is a non-homogeneous system of linear equation is said to be consistent if rank of A is equal to the rank of augmented matrix, that is the rank of the coefficient matrix is equal to rank of the augmented matrix. So we have given that x plus y plus z is equal to alpha, x plus beta y plus z is equal to gamma, and x plus y plus alpha z is equal to beta has at least one solution. So it is a non-homogeneous system of equation and it has at least one solution. At least one solution means that the system is consistent. The system is consistent means that rank of A is equal to rank of the augmented matrix. Now we are considering our augmented matrix. Augmented matrix AB is equal to 1 1 1 alpha 1 beta 1 gamma 1 1 alpha beta. Now we are writing the augmented matrix from here, and the coefficient of x y z, so 1 1 1 and here the alpha. Okay, similarly the rest of these elements. Now we are applying, now we are row reducing. So our first row can no change, and our second row will be changes to R2 changes to R2 minus R1, and the third row will changes to R3 changes to R3 minus R1, then which is similar to our augmented matrix is similar to 1 1 1 alpha 0 beta minus 1 0 gamma minus alpha 0 0 alpha minus 1 beta minus alpha. Okay, so our augmented matrix is similar to this matrix, and put it as equation number 1 for future reference. We are like, now if alpha is equal to 1, Okay, now alpha is equal to 1. Now alpha is equal to 1, then the augmented matrix become 1, 1, 1. Here the position alpha, so alpha become 1 and 0, beta minus 1, 0, gamma minus alpha. So we putting alpha is equal to 1, gamma minus 1 and 0, 0, 0, beta minus alpha, so beta minus 1. Now we are supposing if beta not is equal to 1, then the augmented matrix is similar to 1, 1, 1, 1, 0, k, 0, gamma minus 1, 0, 0, 0, k. Because I taking beta not is equal to 1. Beta not is equal to 1 means this term b minus 1 will come non-zero. So I taking a non-zero term k, and also we are taking a non-zero term k. So now we are considering this portion, this matrix. We are considering this matrix. So the last row is 0. So here only two linearly independent rows. So the rank of this matrix is 2, and by here we have a non-zero entry. Therefore we have the rank of the augmented matrix is equal to 3. Therefore we get rank of A is equal to 2 and rank of augmented matrix is equal to 3. That is, we have said that rank of A which is not is equal to rank of the augmented matrix A with B. Therefore, but we given that our system has consistent, our system consistent means our system has at least one solution. Therefore we must we have a rank of A is equal to rank of AB. For that beta must be 1. If beta is equal to 1, then this term will if beta is equal to 1, this term becomes 0, and also if beta is equal to 1, this term becomes 0 and this term becomes 0. So the okay, 0. So we for that for making rank of A is equal to rank of AB, we must have beta is equal to 1. That is, if beta is equal to 1, then the rank of augmented matrix is equal to 1, 1, 1, 1, 0, 0, 0, gamma minus 1, 0, 0, 0, 1. If gamma not is equal to 1, then the augmented matrix become 1, 1, 1, 1, 0, 0, 0, some k, 0, 0, 0, 0. Because we are choosing gamma not is equal to 1, so here we have a non-zero term. So when we again considering this matrix, that is this matrix, while considering this matrix, we have rank of this matrix is equal to 1, because here only one linearly independent row, and the rank of the augmented matrix is equal to 2. Therefore we have rank of A which is not is equal to rank of the augmented matrix. But it is not possible because our system is consistent, because it has at least one solution. Therefore rank of A is equal to rank of the augmented matrix. Therefore our assumption, if rank not gamma not is equal to 1 is wrong. Therefore we must have gamma is equal to 1. So if gamma is equal to 1, then this term will be also 0. Then rank of A is equal to rank of augmented matrix AB, which is equal to 1. Therefore our first condition, which says that if alpha is equal to 1, then gamma is equal to 1. Okay, therefore it is a true condition. So our first option is correct. Now for the second option, for B, if beta is equal to 1, our first matrix, that is our row reduced form will become that the augmented matrix B, which is similar to 1, 1, 1, alpha, 0, 0, 0, gamma minus alpha, 0, 0, alpha minus 1, 1 minus alpha. Okay, that is, if B is equal to 1, then our 1 become like this. Here we see that the rank of, by considering this, rank of A is equal to 2 and the rank of augmented matrix is equal to 3. So we want to, our system is consistent, so to make rank of A is equal to rank of augmented matrix AB, we must have alpha is equal to gamma. That is, when alpha is equal to gamma, this row completely 0. Therefore this matrix have rank 2, and also the whole matrix, augmented matrix, has also rank 2. Therefore to make a consistent, we must have alpha is equal to gamma. Therefore our second option, if beta is equal to 1, then gamma is equal to alpha, which is a true statement. So our second option is also correct. Now for the third option, if beta not is equal to 1, for the third option we have the condition beta not is equal to 1. So I just choosing beta is equal to 2, then the augmented matrix AB, which is similar to the matrix 1, 1, 1, alpha, 0, beta minus 1, 0, gamma minus is alpha 0 0, alpha minus 1, beta minus alpha. When we substituting beta is equal to 2, which will similar to 1 1 1 alpha 0 1 0 alpha, sorry, gamma minus alpha 0 0 alpha minus 1 and 2 minus alpha. Here the rank of A is equal to 3 and rank of augmented matrix. Here rank of A is equal to 3, which is equal to rank of the augmented matrix A with B. When alpha is equal to 1, this become, when alpha is equal to 1, this augmented matrix AB become 1 1 1 1 0 1 0 gamma minus 1 0 0 0 2. Now here rank of A is equal to 2, which is not is equal to rank of the augmented matrix, which is equal to 3. Because our third option, which says that beta naught is equal to 1, beta naught is equal to 1, then alpha is equal to 1. Okay, then beta naught is equal to 1, we are for a corresponding beta is equal to 2, we get a rank of A is equal to 3 and a rank of A augmented matrix. But when we substituting alpha is equal to 1, we get rank of A is equal to 2, which is not is equal to rank of the augmented matrix. But our system is consistent because our system has at least one solution, so our third option is also wrong, which is not possible. Now for the last option D, if beta is equal to 1, the augmented matrix AB, which is similar to 1 1 1 alpha 0 0 0 alpha gamma minus alpha 0 0 alpha minus 1 1 minus alpha. So here we have rank of A is equal to 2 and the rank of the augmented matrix AB is equal to 3. If alpha is equal to 1, this become the augmented matrix become 1 1 1 1 0 0 0 gamma minus 1 0 0 0 0. So from we can see that the rank of this matrix, that is rank of A is equal to 1 and the rank of the augmented matrix AB is equal to 2. Therefore rank of A, which is not is equal to rank of the augmented matrix. Therefore we can say that the system has no solution. Our last option is say that if beta is equal to 1, then alpha is equal to 1. So when beta is equal to 1, we get like this. When if alpha is equal to 1, we get it like this. So this our condition, one condition is our system has at least one solution which does not satisfy. So our last option, if beta is equal to 1, then alpha is equal to 1 is a wrong option. Okay, so the correct option of this question is option number A and option number B. Okay, thank you. If you like my video, please subscribe my channel and also share and like.